Okay, for the last part of part C, to make the pair of C4 and C4 star, I want everyone to create a plain cyclohexane chair conformation. Okay, how do we know it's chair? Again, you'll be able to see with a certain angle, you'll have this headrest and footrest. At the same time, you'll have components going vertically up or vertically down, which are your eggshell components, and you'll have these little components that are radiating outwards of the ring, your equatorial components. Okay, so there. Once you have this cyclohexane, plain cyclohexane, this time the hydrogens are no longer color-coded, everything's just black and white. I want you to look for the headrest. Put it on the rightmost of the molecule and make sure that the headrest, okay, is on the rightmost, and you'll take its hydrogen on an eggshell up position and you'll replace that with a blue nitrogen. Okay? And then from that position, you will count, or you will treat this as position number 1, and then you will count to 4, going around the whole structure and counting each carbon. So 1, the carbon with nitrogen, 2, 3, 4. You'll notice that position number 4 is actually the footrest carbon. So I want you to pull out the equatorial up hydrogen of that footrest carbon and replace it with the red oxygen atom. Sorry, not oxygen. This is now going to be a red bromine atom. So bromine can also be represented by red. Okay, this will now be bromine and this will be nitrogen. So I want you to pause right now, look for the periodic table in the classroom, and tell me which atom is larger or heavier. Is it bromine or is it nitrogen? And therefore, which atom is bulkier and larger and takes up more space and therefore will repel other atoms way more? Will it be bromine or will it be nitrogen? Okay. So once you have this model, I want you to be able to draw this or turn this into a skeletal structure. Again, you'll have to start off with a chair, but this time maybe you'll avoid having your hydrogens shown. We know that on the headrest position, we have a eggshell up nitrogen. And on the footrest position, which is carbon 4, we'll have a red bromine atom on an equatorial up position. So notice how this nitrogen is on an eggshell up position and this bromine is an equatorial up position. Because nitrogen and bromine are both on an up position, nitrogen and bromine are said to be in a cis position to each other. In fact, this molecule is a cis molecule because nitrogen and bromine are both pointing up, even though it looks like they're not really pointing in the same direction. One's going upwards, one's going outwards. It doesn't make sense that this is cis, but if you consider that they're both pointing up, in quotation marks, their general positions are both going up, then we can say that bromine and nitrogen are cis to each other. Once you've created this structure and you've drawn this skeletal structure, I want you to then perform a chair flip. So go from chair to boat to chair, just like we did in the last example, and I want you to draw the resulting skeletal structure. You will then answer the question of, how did you interchange the two chairs? Did you have to break any bonds or did you simply have to rotate bonds? But the more important question really is that which among the two chair flip forms, C4, this one here, or its chair flipped C4 star? Recalling our previous lecture or idea that I just brought up actually, that having large components in an eggshell position is very destabilizing, making a molecule less stable, making it a higher energy molecule. And having larger atoms and molecules in groups branch out from the equatorial position gives them a good chance of not having direct repulsion with other atoms in the vicinity. So with that, you've just performed what's called a conformational analysis by looking at the different conformations and even isomers and possible structures of different sets of molecules, and by comparing the amount of steric hindrance and repulsion, among other things, we can determine the different relative energy levels of a molecule based solely off its three-dimensional structure. If you have any more questions or if certain things are unclear, again, please do your best to consult the material on Canvas. If not, you can look for tutorials on YouTube. And finally, you can always bring these things up when you all meet with me again in our next lecture class.